और भैया भी कर भी कहीं कुछ भी करता है ना, तो कुछ बस थोड़ी सी सब्जी और आटा लगाएंगे भैया को पूछ लो। हाँ,
गुड इवनिंग, गुड इवनिंग. Am I audible? Please confirm. So without any delay, I am starting the class. So namaskar, adab, satyakal, 𝐂𝐤𝐴𝐻, hello and welcome in GATE Wallah. So in this lecture, in this series, we can say, we will cover various topics or chapter of the subject vibrations. Okay. What I will try to do in one class, I will try to complete one topic. Like today, we will discuss natural vibration or free undamped vibration of single degree of freedom system. So today we will going to cover this topic, that is natural vibration of single degree of freedom system. Okay. Yes. So which topics we are going to cover today? Mainly, first of all, introduction of this natural vibration. Then we'll discuss natural vibration of general spring mass system. Okay, then in mainly natural vibration, the question comes regarding the calculation of natural frequency. And for calculation of natural frequency, after discussing natural vibration of general spring mass system, we'll discuss calculation of natural frequency by using some methods, like we'll discuss equivalent stiffness method, then we'll discuss equilibrium method, then we'll discuss energy method to calculate natural frequency. Okay, so I'm going to cover one by one. So first we'll discuss introduction. So in introduction, what is natural or free undamped vibration? To discuss that, I am taking this as our example. Suppose this is a spring. Right now we are assuming this spring is massless. Suppose the stiffness of this spring is K. And with this spring, one point mass M is attached. Okay. Okay. Right now we are assuming this surface is frictionless. Right now this is mean position of the system. Yes. Very good, sir. This is mean position of the system. Now what we are doing, we are displacing this mass from its mean position by applying a impulse force. Impulse force, I am applying this force for a very short duration. What I am doing, I am applying a impulse force, okay, and I am disturbing this mass from its mean position. Okay. Now after disturbing this mass from mean position, suppose we have brought this mass by applying this impulse force at this location. After that, I have released that force. Now what will happen when I will release that force? Now this system will vibrate like this. Means what will happen once after disturbing this mass from its mean position, and whatever force I have applied to disturb this mass from mean position, if I will release that force, what will happen? This mass will go towards mean position. But you will say, sir, when it will reach to mean position, it should stop. But it will not stop at mean position. After that, when it will reach to mean position, now it will go disturb in other side. Okay. Okay. And in other side, after reaching one position, again it will come back to its mean position and it will vibrate. It will have to and fro motion like this. And this to and fro motion is known as vibration. Okay. Now you will say, sir, why it is occurring? Why it is occurring? So in very brief, I am discussing first. What will happen now? Suppose first I disturb this mass from its mean position from mean position by applying impulse force. But whatever force I have applied, I have released that force. So now what will happen now? At this position, it will try to come back to its mean position. Reason? See, when I disturb this mass from mean position, suppose I disturb this mass from mean position by x distance. Okay, this distance is x. So what will happen? This spring will also elongate by x amount. So here spring force will come, which is k into x. And since I disturb the mass from mean position toward this direction, so spring force will act in this direction. Okay. So this force is known as restoring force. The force which is trying to bring this body towards its mean position is known as restoration. Here restoration is occurring due to stiffness, because due to this spring force, it will try to come back to its mean position. So due to the presence of this restoring force, because whatever disturbing force I applied here, now I have removed that force now. So due to this restoring force, it will try to come back to its mean position. Okay, good. Now, when it will come back to its mean position, what will happen? Its velocity will increase because net force is acting in this direction. So what will happen? Since net force is acting in this direction, so net force is equal to mass into acceleration. So acceleration will also come in this direction, and due to that acceleration, its velocity will increase. Now what will happen? When this body will reach to mean position, just try to understand the concept. Okay, at mean position, no restoration X. But what will happen when it will reach to mean position? It will have some velocity, because when this body was going towards mean position, its velocity was increasing. So it will have some velocity, and direction of velocity will be towards this side. So now what will happen? Due to this velocity, or you can say due to this kinetic energy, now this mass will move in this direction. Okay. Now see, when this mass is going in this direction, so again can I say this mass is moving far away from mean position. Okay, so what will happen now? When this mass will go in this direction, just try to imagine when it is going in this direction, here restoration force acts, will again act, and it will act in this direction because restoring force will always be towards mean position. So what will happen when it is going in this direction? But since restoration in this direction, the velocity of mass will decrease because motion is opposite to the restoration. Okay, and when velocity is increasing, it will reach to a position when velocity will be 0. So suppose here velocity is 0. Okay. Now, since here velocity is 0, so body should stop here. Yes, but it will not stop here. Reason? Because it is not its mean position. So at this position, restoring force is acting, which is acting towards mean position, means in this direction. And due to this restoration, again it will move towards mean position. Okay. And when it will move towards mean position now, again its velocity will increase. Reason? Because restoration is acting in the direction of motion. Okay. So since its velocity is increasing, so when it will reach to its mean position, its velocity will be maximum, but now the direction of velocity will be towards this side. And due to this velocity, again it will move in this direction, and this motion will continue. Okay. If there is no loss in energy during this motion, okay, right now we are assuming there is no resistance, no friction, no resistance is provided by air. I am assuming it is in vacuum. So if there is no resistance, what will happen? During motion, total energy will be constant. And if total energy is constant, this to and fro motion will occur infinite times. Okay, and this motion is known as vibration. And if there is no loss in energy, this is known as undamped vibration. Undamped vibration. Second thing is, if during vibration, no external force acts. Right now you can see, whatever force I have applied in this body to disturb the body now, I removed that force. Means can I say in this vibratory system during vibration, no external time dependent force acts? So if during vibration, no external time dependent force acts, that vibration is known as free vibration. In upcoming class, I will discuss force vibration also. But today we are going to discuss free vibration. Free vibration means during vibration, no external time dependent force acts. So it is free vibration. And second, if there is no resistance in vibration, okay, we are assuming it is in vacuum, means neither there is any device which is applying resistance in vibration, and we are neglecting the resistance provided by air also. Means there is no resistance in vibration, then it is known as undamped. Because if there is some resistance, that will known as damped. So since today we are discussing undamped, so it is free undamped vibration, and free undamped vibration is also known as natural undamped vibration and sometimes natural vibration. So this is natural vibration. In natural vibration, one important effect acts, which is known as restoration. Okay, here restoration is occurring due to stiffness. Okay, so this is the brief introduction about natural vibration. Okay, what is vibration? If I will disturb this mass from its mean position, then I will reach, it will have to and fro motion. This to and fro motion is known as vibration. Now in this vibration, if during vibration no external time dependent force acts, second there is no resistance, then that vibration is known as natural vibration. Okay, yes. Now for this natural vibration, first I am going to discuss this natural vibration, or you can say free undamped vibration of single degree of freedom spring mass system, and in spring mass system also I am taking general case. Because why I am first discussing general case? Because whatever final result will come for general case now, will remember that result. And if you understood the result for general case, then if question is coming from other cases also, okay, other case means whichever case I am discussing in general case, apart from this any other question is coming, you will be able to solve those question also. But I will remember the result of general case. What is general case? The example which I have taken right now. General case means one massless spring, suppose the stiffness of this spring is K, is directly attached to a point mass, suppose M. Okay, and this mass is vibrating in the direction in which spring is aligned. Like right now spring is aligned in horizontal direction, so this mass is vibrating in horizontal direction. So this is known as general case of natural vibration. Okay, okay. Now after that, this diagram is horizontal, vertical, it doesn't matter. Suppose if you are keeping this system like this also, this is also general case. Why? A massless spring is attached to a point mass. After that, mass is vibrating in the direction in which spring is aligned. Okay, so this is also whether you are taking case A, diagram B, both are same. Only you have to ensure a spring is directly attached to a point mass and mass is vibrating in the direction in which spring is aligned. If you want, you can draw the diagram like this also. It is also general case. Why? Because a spring is directly attached to the point mass and mass is vibrating in the direction in which spring is aligned. Okay. Now, whenever we are discussing any cases now, I need to derive the governing equation of that vibration. Governing equation means first I am discussing deriving that equation for this general case. Okay. For derivation, I am taking this diagram as my reference. A spring of stiffness K is directly attached to the mass M, and mass is vibrating in the direction in which spring is aligned. Yeah. Now for this case, I am doing the derivation. See, okay, suppose right now this is mean position. So to derive the equation of vibration, I am taking any position in which this mass has disturbed by x distance from its mean position during vibration. Right now I am taking x in this direction, that is horizontal route, right? Okay. So now we will draw the FBD of this mass M for this disturbed position. Disturbed position means when this mass is disturbed by x distance from mean position. So suppose here I am drawing the FBD. This mass M, with this mass, this spring is attached, whose stiffness is K. I am cutting the spring from this location. Okay. So first force which we will apply here is restoring force or spring force, because here restoration is occurring due to stiffness. How we can calculate restoring force? See, the stiffness of the spring is K. Now see this displacement of this spring from mean position. So right now displacement of mass from mean position is x, and this spring is directly connected to the mass. So can I say displacement of this spring from mean position is also x? So here restoring force will be K into x, stiffness into displacement. Okay, and its direction will be opposite to x. Right now x is in this direction, so restoring force will be in this direction. Okay, so this is restoring force. Okay, no other spring is attached, so restoring force is completed. Okay, but here now, since vibration is occurring, means can I say actually this system is not in equilibrium? Yes. And if this system is not in equilibrium, if any system is not in equilibrium, in that system, if you want to use the equation of equilibrium, we need to apply a force which is known as pseudo force or inertia force. This is nothing but D'Alembert principle. You have studied these things in your 11th level mathematics. What is pseudo force or inertia force? Suppose in any system, any mass is involved, any point mass is involved whose mass is m. It is having some acceleration. Suppose acceleration of the mass m is a. Then if you want to use equilibrium equation for that system, you need to apply a pseudo or inertia force whose expression is always mass into acceleration, that is m into a. And direction of this inertia force will always be opposite to acceleration. Okay, and after applying this pseudo or inertia force, you can use the equation of equilibrium. It is valid for all type of system. Okay, so right now you can see the displacement of this mass m, pseudo or inertia force which will apply for that body whose mass is involved, whose mass or inertia is given. So this mass is having inertia because it is having mass m. Now the displacement of this mass from mean position is x. So can I say its velocity will be x dot? X dot means dx by dt. Differentiate this x with respect to time. Its acceleration will be x double dot. X double dot is nothing but dx dot by dt. Okay, or you can say d square x by dt square. So acceleration will be x double dot. Okay, now what about direction? See, if you are calculating x double dot or acceleration by differentiation, the direction of x double dot will always be same as x. Right now x is in this direction, so x double dot will also be in this direction. But you can argue, sir, it might be possible actual acceleration is acting in this direction or actual acceleration can also act in this direction. Then why you are saying x double dot is in this direction? See, whenever you are calculating acceleration by differentiation, its direction will always be same as x. Now remember, if actual acceleration is in this direction, automatically the value of x double dot will come positive. But if actual acceleration is in this direction, in that case, automatically value of x double dot will come negative. Suppose if acceleration is in this direction, its value is 5. So can I say acceleration is in this direction with value minus 5? So when actual acceleration is in this direction, automatically x double dot will come negative. Means the direction of x double dot will always be like this. Means it will be same as x. Okay, you can remember this. This is mathematics. So direction of x double dot is always this. So here inertia force will come, which will be mass into acceleration. So mass is m, acceleration is x double dot. And can I say this will be opposite to x double dot? Right now x double dot is in this direction. So inertia force will be in this direction. Okay. Now in the direction of vibration, no other force is acting. And since we have applied inertia force, so you can use the equilibrium equation. Equilibrium equation after applying inertia force. Here all forces are acting in x direction. So I can use this equation, summation of force in x direction equal to 0. And while using this equation, since all forces are coming in this direction, I am adding this side force. And if you are adding this side force, then subtract this side force. So mx double dot is acting in this side, which I am adding. So plus mx double dot. Kx is acting in this side. So plus kx equal to 0. So this differential equation is known as governing equation for natural vibration. And if it is the case of general spring mass system, you can remember this equation. Governing equation will always be like this. General case means a spring is directly attached to the mass and mass is vibrating in the direction in which spring is aligned. If this case is coming and if disturbance of mass from mean position is x, governing equation will always be like this. Mx double dot, you can remember this in your mind. Plus kx equal to 0. Means here in this equation the coefficient of x is k, which is nothing but stiffness of this spring. Coefficient of x double dot is m, which is nothing but the value of this point mass m. Okay, so this is governing equation. Mx double dot plus kx equal to 0. Okay, now if I am saying it is the governing equation for general case, I derived this equation for case A, but this equation is valid for case A also, case B also, and case C also. I am just proving this. If you have derived this equation for case B also, you will get same equation. I am just for understanding, I am proving this. But at last will remember, if it is general case, whether diagram is like this or like this or like this, governing equation will always be this. You need not to do derivation. Just for understanding, I am doing this derivation for diagram B also. But again, same equation will come. Okay, see. Here, this is the spring. With this spring, a point mass m is attached directly and mass is vibrating in this direction. Okay, but here what will happen first of all, this is the mean position. For vibration will disturb the mass from mean position, but that is different thing. But here you can see at mean position also there will be some static deflection in the spring due to the weight of mass. See here in this diagram, at mean position there was no deflection in the spring. Reason? Because weight is acting in vertical direction. Okay, means no component of weight is acting in this direction, so there will be no deflection in the spring. But here due to the weight there will be some static deflection in the spring. Now due to weight or due to static force, whatever deflection is coming in the spring, that is known as static deflection. Okay, if you want to find that, you can easily find. How? See, suppose before applying this mass here, this is the diagram of spring. Okay, now what will happen when I am applying this mass? Due to the mass, weight will act in vertically downward direction like this. Yes, and due to this weight, this spring will elongate, and after reaching this position, it is coming into equilibrium because this is mean position. So suppose till reaching the mean position, the deflection of the spring is delta, and after this static deflection delta, it is coming into equilibrium. Okay, and since this is equilibrium or mean position, at this position net force will be 0. So how I can find the relation between mg and delta? See, first of all, at this position, this weight is acting in vertical downward direction. At this position, spring has elongated by delta amount. Stiffness of the spring is K. So can I say spring force will be K delta? In the abridged of mass, it will be opposite to deflection. Right now, delta is downward. So can I say it will act in upward direction? And since it is mean position, at this position net force will be 0. So now suppose I am using summation of force in vertical direction equal to 0. And while using this equation, suppose I am adding upward force, then will subtract downward. So K delta is upward, which I am adding. Mg is downward, so minus mg equal to 0. So can I say here mg is equal to K delta? Mg is equal to K delta, because we know net force at mean position will always be 0, and if we are using that equation, we are getting mg is equal to K delta. Just remember this. Okay, but ultimately my objective is to derive the equation of vibration. Yes sir. Now to derive the equation of vibration, now what we'll do, this time discussing just for understanding, nobody will explain this. Now I am taking any position during vibration in which this mass has disturbed by x distance from its mean position. See, x is not total displacement of the spring. X is the displacement of spring for mean position. That is very important. Okay, and right now we have taken x downward. Okay, now if the displacement of spring from mean position is x, so can I say the velocity or displacement of mass from mean position is x, so its velocity will be x dot, acceleration of the mass will be x double dot, and since we are calculating x dot and x double dot by differentiation, direction of x dot and x double dot will be same as x. Okay, now here apply the force which is coming in this diagram, okay, to derive the equation of vibration. So first of all, definitely weight will act, mg. Why I am considering weight? Because it is acting in the direction of vibration, and we had to take all the force which is acting in the direction of vibration. Okay, now what about spring force? So don't say here spring force will be kx. No, so sir. See, can I say at this position the total deflection of the spring is delta plus x, where delta is the deflection of spring at mean position and x is the displacement from mean position. But ultimately total deflection is delta plus x. So can I say here spring force will be k in bracket delta plus x, and direction of delta plus x is downward, so it will act in upward direction. Okay, but instead of this now, you can ultimately you can write like this now, k delta plus kx, both are in upward. You can apply this force also like this. Okay, first calculate the spring force at mean position. At mean position deflection is delta, so spring force will be k delta. Delta is downward, so it will be upward. Okay, now can I calculate the spring force which is coming due to the deflection from mean position. So can I say deflection of this spring from mean position is x. So due to this amount, spring force will be kx. It will be opposite to x. X is downward, so it will be upward. Why I am writing like this, you will understand later. Okay, so I have written this in two parts: k delta, which is spring force of mean position, kx, which is the spring force due to the displacement from mean position. And if you add them, this you will get total spring force. Okay, but here right now you cannot use equation of equilibrium because it is not equilibrium position. So to use equation of equilibrium here, I need to apply pseudo or inertia force. And how I can apply pseudo or inertia force? For that, see, the mass of this body is m, acceleration is x double dot, so inertia force will be mx double dot. It will be opposite to x double dot. Right now x double dot is downward, so it will be upward. And after applying this pseudo force, now I can use equation of equilibrium. So suppose in this displaced position I am using this summation of force in y direction 0, and y using this, suppose I am adding upward force, then will subtract downward. So see, k delta is the upward which I am adding, kx is also upward which I am adding, you can see, mx double dot is also upward which I am adding, and mg is downward which I am subtracting. So minus mg equal to 0. Now see, I already proved that mg and k delta are same. So this two part will get cancelled. And after cancelling this, we are getting the equation mx double dot plus kx equal to 0, which is same as this equation. That's why I was saying this is also general case. This is also general case. Okay, when one spring is attaching to the mass, after that mass is vibrating in the direction in which spring is aligned. After that, it doesn't matter whether diagram is horizontal, vertical or inclined, the governing equation will always be like this. Okay. But if you are doing this derivation, now we'll remember this. But if you are doing this derivation, you can see now for this second case, derivation was very lengthy. Reason, because in this derivation we have considered weight also, we have considered this static deflection also. After that, we have cutted this part. But see, before applying this now, I was already knowing that here mg and k delta will be same, they will cancel each other effect. So see what conclusion I am trying to make. Whenever in any system now, if weight is acting in the direction of vibration, but due to that weight, there is some static deflection in the spring, then you can remember they will cancel each other effect. Okay, like here, due to weight, there will be static deflection in the spring, but how much static deflection is occurring, don't calculate that part. Simply remember in your mind, if in the direction of vibration weight is acting and due to weight some static deflection is coming in the spring, they will cancel each other effect. And if they are cancelling each other effect, don't do any calculation, just remember, in that case there will be no role of gravity in the restoration, because here in this equation weight is not coming na? So there will be no role of gravity in the restoration. And if you are confirmed that there is no role of gravity in the restoration, during derivation of vibration equation, neither you need to consider weight, nor you need to consider spring force which is coming due to static deflection, because they will cancel each other effect. But how they are cancelling, don't bother about that, because even if you consider those forces, ultimately that will get cancelled. What I am trying to say, see, this spring is directly attached to the mass. Good. Mass is directly vibrating in the direction where spring is aligned. So in this case, it is true, weight will act in the direction of vibration, but due to weight there will be static deflection in the spring. And if due to weight there is static deflection in the spring, just do this in your mind, they will cancel each other effect. And since they will cancel each other effect, you can write separately, there will be no role of gravity in the restoration. And if there is no role of gravity in the restoration, during the derivation of vibration equation, neither will consider weight nor will consider static deflection. They will cancel each other effect, but how they are cancelling, don't bother about that. Okay, just okay. So suppose now what is the static deflection of the spring at mean position? Don't bother about that. Suppose this is mean position, and during vibration take any position in which this mass is disturbed by x distance from mean position. It is disturbance from mean position, and if disturbance from mean position is x, velocity will be x dot, acceleration will be x double dot, direction of x double dot and x dot will be same as x. And since spring is directly attached to the mass, so can I say displacement of spring from mean position is also x. It is from mean position, not total deflection. Now here, which force will apply? First apply restoring force. And here restoration is occurring due to stiffness only. So how we can calculate restoring force due to stiffness? See the stiffness of this spring, it is K. Now its disturbance from mean position, it is x. So restoring force will be Kx. In the body of mass, it will be opposite to x. Right now x is downward, so it will be upward. Completed. Neither will consider weight nor will consider static deflection, because they will cancel each other effect, but how they are cancelling, don't bother about that. Okay. Now to use the equation of equilibrium, we will apply pseudo force. Pseudo force will apply for that body whose mass is given. So mass of this body is m, acceleration is x double dot, so pseudo force will be mx double dot. It will be opposite to x double dot is downward, so it will be upward. After that, use this summation of force in y direction equal to 0. And while using this, suppose I am adding upward force and subtracting downward. So mx double dot is upward plus kx upward, that is equal to 0. Same equation I am getting. Clear? So first important conclusion is for general spring mass system. General means spring is directly attached to the mass and mass is vibrating in the direction in which spring is aligned. After that, it is horizontal, vertical, inclined, it doesn't matter. The governing equation of vibration is mx double dot plus kx equal to 0. For general case, the coefficient of x double dot is m, which is the value of this point mass. You can remember, just remember this. The coefficient of x is k, which is the stiffness of the spring. Yes. This is first important conclusion. Now see, this is the equation. Now, this is differential equation. So now this is mathematics. Will solve this equation. In mathematics, you have studied now how to solve differential equation. And when you will solve this equation, you will get the solution, that is x as a function of time. Okay. But this is mathematical part now. So I am not going in the calculation of mathematics. If you solve this equation now mathematically, when you will solve, you will get the equation of x as a simple harmonic function. Simple harmonic means you will get this equation as a sine function or cos function. Okay, I am not going to derive. Whenever you solve the problem of natural vibration of single degree of freedom, solution of x will always be like this. It will be like this: a sine omega t plus phi. Okay, this is periodic function. Okay, whose amplitude is capital A. This is amplitude, and we know in natural vibration, vibration will occur with constant amplitude. So you can see amplitude of this equation is constant. What is omega? I will draw the graph of this equation. Omega is the frequency of this equation in radian per second. Whenever any equation you are written like this, that is known as simple harmonic. I am not going in too much detail because in YouTube class we are discussing in brief manner. But you will be able to solve all the problem if you will understood this. So omega is known as frequency of this equation in radian per second, and phi is known as phase angle. Okay. Now, whenever we are discussing natural vibration, the frequency of natural vibration in radian per second, generally I will denote as omega n. It is my notation, n for natural vibration. So instead of omega, I am writing omega n. Okay. You will get this equation for all single degree of freedom natural vibration system. Always solution will be like this. Okay. Now, what about omega n? It will calculate this omega n for general case. Right now we are discussing for general case. The formula to calculate omega n is root k by m. Where k is, you can remember this. Now for general case, omega n is always root k by m. Where k is nothing but the stiffness of this spring, n is value of this point mass m. For general case, you can, as per this equation, you can say k is the coefficient of x, that is displacement, and m is the coefficient of x double dot, which is in this case it is equal to mass. For general case, k is stiffness, m is mass. Okay. So this omega n is known as natural frequency or natural undamped frequency of natural vibration of single degree of freedom system. And if it is general case, the formula to calculate omega n is root k by m. But what about a and phi? You had discussed the expression of omega n. But what about a and phi? Here a and phi are arbitrary constant. Because whenever we are solving double order differential equation, in the final solution always two arbitrary constant will come because it is double order. Arbitrary constant means they are constant. But right now we cannot tell what is the value of this constant because that will depend upon boundary condition. So to calculate a and phi, boundary condition is required. So whenever examiner will ask a and phi, he will give boundary condition. Right now a and phi are arbitrary constant. So right now you can only calculate this omega n. For general case, formula to calculate omega n is root k by m. It is natural frequency of the system in radian per second. Okay. If we draw the graph of this equation, graph will be like this. Means in natural vibration always motion will be like this. In y-axis I am taking displacement x. In x-axis I am taking time. Okay. See, this is periodic function. Periodic function means here sine is coming. So we know sine term always repeats after 2 pi angle. Okay. So can I say this is constant? It is variable, na? So whenever, see, when omega and t, suppose when omega and t is alpha. Similarly, when omega t is 2 pi by 2 pi plus alpha, what I am trying to say, this expression of x will come same. Means sine alpha plus phi and sine 2 pi plus alpha plus phi are same, because sine 2 pi plus theta is sine pi theta, because after every 2 pi angle sine repeats. So can I say when after every, whenever omega n into t is 2 pi, this equation will repeat. Okay. So whenever, can I say, whenever time is equal to 2 pi by omega n t is 2 pi, means time is equal to 2 pi by omega n. So after every this interval, this equation of x will repeat. So this is known as time period. Time, and I think you already know this equation. Whenever frequency is omega, time period will be 2 pi by omega. So after every this time cycle, graph will repeat. So this is known as time period. Okay. Now if you draw the graph, now see here, if you put t equal to 0, it is a sine phi. Now phi, right now I don't know the value of phi. So suppose a sine phi is coming somewhere here. Okay. After that, what will happen now? If you increase the time, initially x will increase and some interval will come in which x will be equal to plus a. Now x cannot be more than a. So after that x will reduce. After some time it will become 0. After that this graph will go in negative direction. And after some interval it will become x will become equal to minus a. Minus a means this height is again a, but it will be on negative side. After that again x will increase. But after this time 2 pi by omega n, this x will reach here, come here. And after that what will happen? This graph will again repeat, because this is one time period. Okay. Now for next time period again you will get same graph. For next time period again you will get same graph. Means what is occurring here? Here this vibration or to and fro motion is occurring with same amplitude. Means amplitude of each cycle will be same, which is equal to capital A. And can I say if natural frequency of this system in radian per second is omega n, for general case the expression of omega n is root k by m, then its time period will be, suppose time period I am denoting as 2n, it will be 2 pi by omega n. Okay. Here you can calculate one more thing. Natural frequency in hertz, because it is natural frequency in radian per second. Na? Natural frequency in hertz I am denoting as Fn. Fn is nothing but, natural frequency in hertz means hertz is nothing but it is cycles per second. Means it is number of cycle completed in 1 second. And natural frequency in hertz will always be a reciprocal of time period. Reciprocal of time period. Now time period is 2 pi by omega, and can I say natural frequency in hertz will be omega n by 2 pi, because it is reciprocal of time period. Why it is like this? Because what is time period? Can I say time period is time required to complete one cycle? Means can I say in tn second, one cycle is getting complete? So can I say in 1 second, 1 by tn cycle will get complete? And number of cycle completed in 1 second is nothing but natural frequency in hertz. So ultimately, if you know natural frequency in radian per second, that is omega n, then you can calculate time period also. You can calculate natural frequency in hertz also. And just remember the formula to calculate natural frequency in radian per second for general spring mass system is root k by m, where k is the stiffness of spring, m is the value of this point mass. Okay. As per this equation, we can say k is nothing but the coefficient of displacement and m is nothing but the coefficient of acceleration. For general case, coefficient of displacement is stiffness of the spring. For general case, the coefficient of acceleration is mass. But you can remember, whenever equation is like this, omega n will be like this. If you know omega n, you can easily write this equation. It is simple harmonic, na? Means solution will always be like this: a sin omega t plus phi. For natural vibration, instead of omega, we are writing omega n. For general case, omega n is root k by m. If you calculated omega n, we can calculate time period also, which is 2 pi by omega n. We can calculate natural frequency in hertz also, which is 1 upon Tn, that is omega n by 2 pi. But this all discussion we had done for general case. But what about other case? Other case means suppose not on more than one spring is involved. Okay, or mass is not point mass, it is distributed mass. So what we'll do for other case? So see, if question is coming for other case, but it is single degree of freedom natural vibration system, what will happen now? The governing equation pattern will always be like this, because for natural vibration solution is always simple harmonic, and if solution is simple harmonic now, if you derive the equation for other case also, now pattern of equation will be like this. Only difference is coefficient might change. Like for general case, coefficient of x double dot is m, coefficient of x is k. But what about the coefficient of x and x double dot for other case? That will come to know after derivations. But pattern of equation will be like this. Pattern of equation like this means suppose the disturbance of mass from mean position I am denoting as x na. So equation will always be like this. X double dot with some coefficient plus x with some coefficient, that is equal to 0. For general case, coefficient of x is k, for a coefficient of x double dot is m. But for other case, what will be the coefficient of x, what will be the coefficient of x double dot, that will come to know after derivation. Suppose right now the coefficient of x I am denoting as k, but don't say k is stiffness. K is just the coefficient of x. For general case, k is equal to k, but what will be k for other case, that will come to know after derivation. Similarly, the coefficient of x double dot I am denoting as me. Me is not mass, it can be mass, it can be mass inertia also. For general case, m is equal to m. For other case, what is me, that will come to know after derivation. But if you are assuming coefficient of x is k, coefficient of x double dot is me, okay, can I say this equation is like this? Only difference is instead of k, k is coming, instead of m, m is coming. So fine, now you can calculate omega n also. Like for general case, omega n was root k by m. Can I say for other case, omega n will be root ke by me? So if you want to calculate this natural frequency for other case now, use this equation root ke by me. K is the coefficient of x, which you will, or displacement, which will come to know after derivation, and m is the coefficient of x double dot, which will know after derivation, and omega n will be root ke by m. For general case, k is k, m is m, but what about k me for other case, that will come to know after derivation. Okay, okay. It doesn't necessarily you always the displacement we will represent as x. If it is having rotational vibration, it might be possible we are representing displacement as theta, but no issue. If here theta is coming now, here theta double dot should come. Like you can also in some problem equation can like also be like this, theta double dot. Again both are same. Coefficient of theta I will denote as ke, coefficient of theta double dot I will denote as me, and omega n will be root ke by m. Both equation are same na. If here theta is coming, here theta double dot. So here x is coming, here x double dot is should come. Here x1 is coming, here x1 double dot should come. Here phi is coming, here phi double dot should come. Here theta is coming, here theta double dot should come. Then all equation are same, and if equation are coming like this, omega n will be root ke by me. Okay. But you will say, sir, to find ke and me, because right now we have remembered for general case that k is k, m is m. But what about for other case? We need to do the derivation. But now derivation is little bit time consuming. But now here I am discussing one method which is known as equivalent stiffness method. By using equivalent stiffness method, now I can calculate omega n even without deriving the equation of vibration. But see, this equivalent stiffness method is not valid for all other cases. Okay, it is valid for some particular type of cases. So remember, first of all, for which cases this equivalent stiffness method is valid. So apply this method only for those cases. But if the question is coming for those cases in which I can apply this method, so what I will do? For those cases, what is the benefit in deriving the equation? Because if we can calculate omega n without deriving the equation. So if those question is coming from those cases now, don't try to derive the equation, just use this method which I am going to discuss right now. First of all, see, this equivalent stiffness method is valid for spring mass system. Spring mass system means restoration is occurring only due to stiffness. Only due to stiffness. Only due to stiffness means there is no role of gravity in the restoration. Second, in that system, only one point mass is involved. Point mass is involved. Suppose the value of that mass is m. It can be m also, it can be 2m also. Right now I am considering it is m. But why I have written? I have written only one point mass is involved. Means only one mass should be there, and that mass should not be distributed mass. It should be point mass. So if we are satisfying this condition that restoration is only due to stiffness, first thing. Second, only one point mass is involved in the system. In that case, to calculate omega n, even you need not to derive the equation of vibration. Without deriving the equation of vibration, you can calculate natural frequency. So what is the formula? If this condition is satisfying, these two conditions, then direct formula to calculate omega n is root ke by m. Just remember, this is equivalent stiffness method. Only one point mass is involved. The value of that point mass is m. So below side write m. Okay, because only one mass is involved. But Ke I need to calculate. Here this Ke is known as equivalent stiffness, and this method is known as equivalent stiffness method. But now question is, how will calculate this Ke? Okay. So in this method now we need to understand how to calculate Ke only. Below side, because in this formula m is coming. But this method is only valid when restoration is only due to stiffness and only one point mass is involved in the system. Okay. Now what is the method to calculate Ke? Here I am writing formula. Method, or you can say now our objective is not to calculate omega n. My objective is to calculate Ke first, because after calculate Ke, put here, you will get omega n. So here in this method, my objective is to calculate Ke. Now formula to calculate Ke is F by delta. It is very simple formula. I am discussing this, and I will discuss with some questions. It will be better clear. Formula to calculate Ke is F by delta. Now what is this? Now what we'll do now? Okay, see. Here delta is, it is the static deflection of the point where, first I am writing, then I will explain, where point mass m is acting. It is the static deflection of the point where point mass m is acting in the direction of vibration, due to static force F which is applied at the location of point mass in the direction of vibration. I am explaining, don't worry. See, what we'll do in this method now, at the point where point mass m is acting, at that point we'll apply a static force F in the direction of vibration. Suppose vibration is occurring in vertical direction. So at the location where point mass is acting, we'll apply static force F in vertical direction. It is your will. In vertical direction, you want to apply downward or upward. If mass is vibrating in horizontal direction, then we'll apply static force F at the location of mass in horizontal direction. Means ultimately in the location where point mass is acting, apply static force F in the direction of vibration. Okay. After that, I have to do nothing with vibration. Only apply F in the direction of vibration. Now after that, it is the question of mechanics. Due to this static force F, we'll calculate the static deflection of the same point. Static deflection means you can use the equation of equilibrium. Because I am not deriving the equation of vibration. Due to this force F, I am calculating static deflection. So calculate the static deflection of the same point where mass m is acting. Okay, and suppose at that deflection I am denoting as delta. Then F by delta is known as Ke, and after calculating Ke like this, put here, you will get omega n. Like suppose I am applying this method for this journal diagram. For journal diagram, I already know finally omega n should come equal to root K by m. Because for this case I had done the derivation. But I am verifying this I am verifying these things by this stiffness method, that same answer is coming or not. See, what I am doing, first of all, this method is valid here or not? Yes, it is valid. Reason, only one point mass is there, and here there is no role of gravity in the restoration. That I already proved, na? Yes. So you can use this method. So now what we will do, at the location where this point mass is acting, it is acting here. Apply static force F in the direction of vibration. Vibration will occur in horizontal direction. So apply static force F in horizontal direction. Suppose I am applying horizontal, right? After that, I have to do nothing with vibration. Now for the same point where you have applied this force F, in this direction, calculate static deflection. Suppose that I am denoting as delta. And since it is static deflection, you can use equation of equilibrium. And Ke nothing but it is F by delta. Okay. Now just do calculation. See, draw the FBD na. F is acting in this direction. I am cutting the spring from this location. Stiffness of the spring is K. Now what will happen? If this mass is going in this direction by delta, this spring will also elongate by delta. So deflection of the spring is delta. So can I say here spring force will come, which will be K delta. Its direction will be opposite to delta. Delta is in this direction. So spring force will be in this direction. After that, I can use the equation of equilibrium, na? Because I am calculating static deflection. So now you can use summation of force in x direction equal to 0. While using this, suppose I am adding this side force and subtracting this side force. So F is this side which I am adding. K delta is this side which I am subtracting, equal to 0. From this, calculate F by delta. It is coming equal to K, and F by delta is nothing but Ke. So for this case, K is coming equal to K, and omega n is root Ke by M, and K is K, M is M. So same answer is coming. But this answer I already know. For general case, I need not to use this method. But just to verify this method is correct or not, I had done this derivation for general case. So here like this you can calculate Ke. Okay. But where mainly we will apply this Ke method? We will apply this method for the other cases in which these two conditions are satisfying. If these are satisfying, by using this formula calculate Ke, put here, you will get omega n. Okay. Now, some questions comes in which spring are arranged either in series or in parallel or in their combination. Now, if spring are arranged in series and parallel, then we have direct formula to calculate Ke. That formula I derived by using these equations. That is, K is F by delta. But if spring are in series and parallel, again you need not to apply this method again and again. You can use direct formula to calculate equivalent stiffness, but that direct formula is valid when spring are arranged either in series or in parallel. Okay. So first I am taking those cases in which spring are arranged either in series or parallel. Like in case 1, I am taking the cases when spring are in series. Like if this diagram is coming, just remember the diagram. This is spring whose stiffness is K1. It is spring whose stiffness is K2. Below this mass is attached. Now see, whenever spring are directly attached to the mass, like here, and mass is vibrating in the direction in which spring is aligned. This condition should always satisfy that mass is vibrating in the direction in which spring is aligned. So you can always use series parallel formula to calculate equivalent stiffness. You can always use. Okay. But how you will come to know that either spring are in series or in parallel? By using this diagram. See, whenever spring is having end-to-end connection, means with this spring, other spring is attached, so it is having end-to-end connection. And below that mass is attached. Okay, so this spring will always be in series. Through this diagram, try to remember this. Okay, means here this spring 1 and 2 are having end-to-end connection. Okay, so they will be in series. In series arrangement, you will calculate deflection of this spring. You will calculate deflection of this spring. If you will add them, you will get total deflection of this mass. But through this diagram, remember, if spring is directly attached to the mass is vibrating in the direction in which spring is aligned. After that, if it is having end-to-end connection like this, they will be in series. And in series arrangement, I am not going to into derivation. What is the formula to calculate equivalent stiffness? Here, spring 1 and 2 are in series. Suppose their equivalent stiffness I am denoting as Ke. So formula to calculate Ke is 1 upon K. Use the reciprocal. That will be equal to 1 upon K1 plus 1 upon K2. Similarly, suppose one more spring whose stiffness is K3 also in series. So here use 1 plus 1 upon K3. You can calculate K. This is for series arrangement. I am not going in derivation. Similarly, case 2. when spring are in parallel. How you will come to know spring are in parallel? Again through diagram. Okay. Remember two type of diagram for parallel arrangement. One is like this. This is spring whose stiffness is K1, his stiffness is K2. With this point mass M is attached and it is vibrating like this. Mass is vibrate if spring are directly connected to the mass and mass is vibrating in the direction in which spring is aligned. You can always use series and parallel arrangement. If they are making diagram end-to-end connection, they are in series. If they are like this, they will be in parallel. Okay. In parallel, deflection of this spring will be same as deflection of this spring, and that is also total deflection of this mass. But you can remember one more diagram for parallel arrangement. That diagram is like this. Suppose this is the spring whose stiffness is K1. With this mass M is attached. Now below this mass, one more spring is attached whose stiffness is K2. Now in this diagram also now, this spring 1 that is K1 and K2 are in parallel. How you can remember? Whenever mass is placed in the middle like this, then the equivalent stiffness of this side system, right now it is K1 because only one spring is coming, and equivalent stiffness of this side system which is K2, they will be in parallel arrangement. Because again if you are try to imagine now, suppose this mass is going in downward direction by delta, this spring will elongate by delta and this spring will contract by delta. Means can I say deflection of this spring is same as deflection of this spring? That is also total deflection of the mass. Means they are having parallel arrangement. But you can remember this diagram. Whenever diagram is like this, they are in parallel. Whenever it is like this, equivalent stiffness of this side system which is K1, equivalent stiffness of this side system which is K2 will be in parallel. And in parallel arrangement, what is the method to calculate Ke? Here K1 and K2 are in parallel. In parallel, the formula to calculate K equivalent, just add the stiffness of individual spring, you will get their equivalent. You will get their equivalent. Okay, so you can solve like this, na? Okay, so that is for parallel arrangement. Okay. Similarly, some case will come in which spring are arranged in the combinations. Just through one diagram I am explaining. Suppose we want to calculate equivalent stiffness of this system. Again, I can calculate by using series parallel because mass are directly attached to the spring and mass is vibrating in the direction in which spring is aligned. But how you can use? So suppose this spring is 1, it is 2, it is 3, it is 4. First of all, we know equivalent stiffness of this side system and equivalent stiffness of this side system will be in parallel. So this side only one spring is coming. So first I need to calculate equivalent stiffness of this side system. And in this side system, 3 spring are coming, na? 1, 2, 3. You can see, first of all, this is here imagination is required. First of all, 1 and 2 are in parallel because their deflection will be same. So first we'll calculate equivalent stiffness of 1 and 2. And can I say equivalent stiffness of 1 and 2 is having end-to-end connection with 3. So with 3 they will be in series arrangement. But for that, first calculate equivalent stiffness of 1 and 2 because they are in parallel. So suppose equivalent stiffness of 1 and 2 I am denoting as K12. Right now don't denote this as Ke because Ke is overall equivalent stiffness. So that's why equivalent stiffness of 1 and 2 I am denoting as K12. How we can calculate K12? So see 1 and 2 are in parallel. So K12 in parallel arrangement to calculate equivalent stiffness, add the stiffness of individual spring. So K1 is 2K, K2 is also 2K. So it is K1 which is 2K plus K2 which is 2K. So K12 is coming 4K. If you want, you can draw equivalent diagram for your understanding. So we are replacing 1 and 2 by single spring whose stiffness is K1. Now with this spring 3 is arranged whose stiffness is 4K. Na? With this mass is attached. Right now I am drawing only the equivalent diagram of this side. After that I will draw for this side. Okay. Now you can see K12 and 3 are having end-to-end connection. Means can I say they are in series arrangement? And since they are in series, I can calculate their equivalent. Here K12 and 3 are in series. So now I can calculate their equivalent. And suppose their equivalent I am denoting as K suffix 1, 2, 3. It is your notation. Okay. Now, since they are in series, how we can calculate their equivalent? 1 upon K123, use reciprocal formula. That will be equal to 1 upon K12. K12 is 4K. I am directly putting the value. Plus 1 upon K3. K3 is also 4K. So 1 upon K123 will be equal to 4K will be LCM. So it will be 1 plus 1, that is 2. 2 upon 4K means 1 by 2K. So can I say K123 will be 2K? Calculation is your partner. Yes. So means we have calculated equivalent stiffness of this side system, which is K123. It is equal to 2K. With this mass M is attached. Now, for this side, only one spring is attached, whose stiffness is K. Only one spring is attached, whose stiffness is K. Okay. Now, can I say this K123 and K are in parallel arrangement? And since they are in parallel, now I can calculate their equivalent. This I am denoting as spring 4. Na? So now K123 and 4 are in parallel. So I can calculate their equivalent. And their equivalent means that is overall K equivalent, because after that no spring are left. And overall equivalent stiffness I am denoting as Ke. And how can calculate Ke? They are in parallel. So just add the stiffness of these two springs. So it will be equal to K123, which is 2K, plus K4, which is K. Okay. So K equivalent is coming 3K. That's it. And after calculating K equivalent, if examiner asking omega, and that is natural frequency in radian per second, it will be root over Ke by m. K is 3K, so it will be root 3K by m. Very simple. Okay. So like this, you can calculate Ke in case of series parallel arrangement. Like solve these two questions. In both the question, our objective is to calculate natural frequency, means natural undamped frequency of the system in radian per second, means omega n. If we calculate natural frequency in radian per second, you can calculate in hertz also, because if we calculate omega n, natural frequency in hertz is nothing but omega n by 2 pi. You can calculate time period also, because time period is 2 pi by omega n. So our main objective is calculation of omega n. Okay. So just solve these two questions. See, I am discussing one by one. First, I am solving this question. Suppose this is spring 1, this is spring 2. Spring mass is directly attached to the spring, so you can use series parallel arrangement to calculate K equivalent. And here 1 and 2 are having N to N connection. So can I say they will be in series? Here 1 and 2 are in series. So how we can calculate K equivalent? Okay. And their equivalent means overall K equivalent, because after that no other spring are left. So since they are in series, I can use this 1 upon K. This will be equal to 1 upon K1, which is 2K, plus 1 upon K2, which is K. Now calculation is your part. LCM of 2K and K is 2K. So 2K divided by 2K, 1 into 1, 1, plus 2K divided by K is 2, 2 into 1 is 2. So it is coming 3 by 2K. So K is reciprocal of this, which is 2K by 3. Yes. So this is equivalent stiffness. And after calculating equivalent, we can calculate natural frequency in radian per second, that is omega, and it will be root over Ke, which is 2K by 3 divided by the value of point mass m, which is m. Okay. So this is natural frequency in radian per second. That's it. If examiner asking in hertz, calculate omega n 2 pi. If examiner asking time period, calculate 2 pi by omega n. Very simple. Yes. So this is natural frequency for this question. Now, what about this question? Here again calculate Ke. Okay, and you can use this approach now, because again the spring are directly attached to the mass, and mass is vibrating in the direction in which spring is aligned. So again use this, you can use this Ke method na, and you can calculate Ke by using series parallel arrangement. How? Suppose this is spring 1, this is 2, this is 3. So first of all, we can say this 1 and 2 are in having parallel arrangement, and their equivalent is making N to N connection with 3. So they will be in series arrangement with 3. But first calculate equivalent of 1 and 2, because they are in parallel. And suppose equivalent of 1 and 2 I am denoting as K12. And how we can calculate K12? See here 1, sorry. spring 1 and 2, they are in parallel. So K12 will be equal to, since they are in parallel, just add the stiffness of individual spring. This will be equal to K1, which is 2K, plus K2, which is again 2K. So how much K12 is coming? It is 4K. If you want to draw equivalent diagram, you can draw, it is your will. Means we are replacing 1 and 2 by a single spring, which is K12, which is equal to 4K. Now with this spring 3 is attached, whose stiffness is 2K, and with this mass is attached. Okay. Now you can see this K12 and 3 are having end-to-end connection. So can I say they will be in series? So now can I say K12 and 3 are in series? So now we can calculate their equivalent, and their equivalent means overall equivalent stiffness, because after that no other spring are left. So means their equivalent means overall K equivalent, which I am denoting as K. And since they are in series, use reciprocal formula. So 1 upon K will be equal to 1 upon K12, which is 4K, plus 1 upon K3, which is 2K. Now calculation is your part. 1 upon K equal to LCM of 4K and 2K is 4K. 4K divided by 4K, 1 into 1, 1, plus 4K divided by 2K is 2, 2 into 1 is 2. So it is coming 3 by 4K. So KE will be 4K by 3. Okay. So this is equivalent stiffness. And after calculating KE, we can calculate omega n, because omega n is root KE by value of point mass, which is m. Now root over KE. K is 4K by 3 divided by m. So value of omega n for this question is root over 4K by 3m. Clear? So like this you can calculate natural frequency of this system. Okay. Next. Okay. But this series parallel formula is only valid when either spring are in series, or they are in parallel, or they are in the combination of series and parallel. Okay. And those cases will come when spring are directly attached to the mass and mass is vibrating in the direction in which spring is in aligned. Okay. But if spring are not directly connected to the mass, like in this diagram, you can see this is the rigid rod, which is rigid and massless. In this rod, spring is attached and point mass is here. Means can I say here spring is not directly connected to the point mass? In that case, neither spring will be in series nor they will be in parallel. So what we will do when spring are neither in series nor in parallel? Very simple. In that case, we will not remember any formula. We will always calculate KE by using this F by delta. Okay. This approach is always valid when only one point mass is involved and restoration is only occurring due to stiffness. Even for series arrangement, the formula to calculate Ke is 1 upon K equal to 1 upon K1 plus K1 upon K2. The formula to calculate K equivalent for parallel arrangement is K1 plus K2. Even we got this formula by using this approach. K is F by delta. K is F by delta. But we have calculated the formula of Ke by using this formula for series and parallel arrangement. So we have remembered that for series, whenever spring are in series, you can directly use this formula for Ke calculation. If they are in parallel, you can directly use this formula for Ke calculation. Okay, but they will either be in series or in parallel when spring are directly attached to the mass and mass is vibrating in the direction in which spring is aligned. But spring is not directly attached to the mass now. In that case, spring will neither be in series nor they will be in parallel. So for that case, I will not remember any formula. Always use this approach, that is Ke is F by delta, and calculate Ke. How? I am discussing with one question that it will be better clear. So I am discussing with this question. For this question, our objective is to calculate the natural frequency, that is omega. But first of all, confirm for omega n calculation I can use equivalent stiffness method or not. So see, in this system only one point mass is involved. How, sir? Because this rod is massless. Because if the mass of this rod is also given then this method is not valid. Because if the mass of rod is also given, that is distributed mass. Okay. Even if this point mass is not there, but if mass of rod is given, suppose it is m, this m, mass of rod is m, again this method is not valid, because this is one mass is coming, but that mass is not point mass, it is distributed mass. But right now, since rod is massless now, or only one point mass is coming here, I can use this method. Reason? Because first of all, see, only one point mass is there, so one condition is satisfying. Second condition was restoration should only be due to stiffness. So here restoration will only be due to stiffness. Reason? See, here what will happen now? Right now you can see this rod is hinged here. This rod is massless, but this weight or mass is attached at the rod. So can I say, if this spring are not there, just try to imagine, if this spring are not there, na, this rod cannot be like this, because due to gravity, na, this mass rod along with this mass will take this position. So can I say, is this rod with this mass is in this position due to the presence of this spring? Means this spring has supported the rod or the mass which is acting in the rod. So what will happen now? What I am trying to explain, try to understand. Can I say, due to the weight of this mass, suppose the weight of this mass is mg, can I say, don't write this, only understand. Due to the weight of this rod mass, there will be static deflection in the spring, because the weight of this system is supported by this spring. So can I say, due to the weight of this mass, weight will always act in vertical direction, but due to the weight of this mass, there will be static deflection in the spring. So see, this I already discussed earlier. Whenever weight is acting in the direction of vibration, here it is acting in the direction of vibration, but if due to that weight there is a static deflection in the spring, and here it will occur, this you can tell by imagination, because this system cannot be in this position without the support of this spring. Means weight of this is supported by this spring, and if weight is supported by this spring, due to the weight there will be some static deflection in the spring. Okay, due to weight there will be static deflection in the spring. Okay, and since due to weight there is static deflection in the spring, can I say they will cancel each other effect? Cancel each other effect means, can I say, in this problem there will be no role of gravity in the restoration. There is no role of gravity in the restoration, because although weight is acting in the direction of vibration, again I am explaining, but since due to weight there is static deflection in the spring, so they will cancel each other effect, and since they are cancelling each other effect, there will be no role of gravity in the restoration. Clear? There will be no role of the gravity in the restoration, because due to weight there is static deflection in the spring, they will cancel each other effect. So in this problem, first of all, we have proved that there is no role of gravity in the restoration. Okay, and means here restoration is only occurring due to stiffness, and since only one point mass is there, I can use this equivalent stiffness method here, because for using equivalent stiffness method there was two conditions. Only one point mass should be there, and restoration should only due to stiffness, it should not be due to gravity. So both conditions are satisfying. But now you can remember this, whenever horizontal rod is hinged at any location and their weight are supported by spring, you can directly remember there will be no role of gravity in the restoration if you want, because due to weight there will be static deflection in the spring, they will cancel each other effect. Along with this, since only one point mass is involved, I can use this equivalent stiffness method. So I am calculating Ke by using equivalent stiffness. I am just drawing this diagram again. This is the mass. Okay. Here one spring is attached, whose stiffness is K. Here one is more spring is attached, whose stiffness is K. This is A. Okay. Now I am not calculating omega and I am calculating Ke. Now because this method is valid. Now for calculation, what we'll do? At the location where point mass is attached here, we'll apply static force F in the direction of vibration. See, when vibration will occur in this rod, it will rotate about this point. Okay, and when it will rotate about this point, this point will move either vertically downward or upward, because it will go like this. So here if I am applying a static force F, I will apply in vertical direction, because this point will move in vertical direction. Now it is your will, in vertical direction you want to apply downward or you want to apply upward. So suppose I am applying in downward direction. Now, after that, I have to do nothing to do with vibration because my objective is to calculate 𝐾𝐸. And for 𝐾𝐸, only apply F at this location in the direction of vibration. After that, you have to do nothing with vibration. Now, due to this static force F, we'll calculate the static deflection of this same point in vertical direction, which I am denoting as delta. And after calculating delta due to this F, the formula to calculate 𝐾𝐸 is F by delta. Now, calculation of delta due to F is nothing but it is mechanics. How we can calculate delta? Now, it is mechanics. See, due to this F, definitely this point will move in downward direction. Now, if it is moving in downward direction, this rod will rotate about O like this, means in clockwise direction. So, draw the FBD after this displacement. Okay. Displacement will be very small, but for to make clear diagram, I am drawing like this. Okay. When this rod will rotate about O, after rotating about O, it will take position like this. This displacement is delta. Okay. Now, suppose the deflection of this point is delta. Whatever notation you are taking now, suppose for deflection of this point, but don't denote with delta because delta is the deflection of this point. So, suppose delta, this is delta 1. Similarly, deflection of this point is delta 2. Why I am focusing on deflection of this point and this point? Because whatever deflection is coming in this point, that is deflection of this spring also. Whatever deflection is coming at this point, that is the deflection of this spring also. Okay. Now, I can find the expression of delta 1 and delta 2 in terms of delta. How? See, you can see this triangle, and this triangle. They are similar triangle. And in similar triangle, ratio of corresponding side will be same. So, how you can find? See, in this bigger triangle, height is delta, upon base is this distance, which is 3a. That will be equal to, in this triangle, height is delta 1, upon base is this distance, which is 2a. That will be equal to, in this triangle, height is delta 2, upon base is this distance, which is equal to a. So, you can find the expression of delta 1 in terms of delta. So, equate both of these two terms. A will get cancelled, 2 will come here this side. So, delta 1 will be 2 by 3 delta. Similarly, I can calculate delta 2 in terms of delta. Equate these two. A will get cancelled, delta 2 will be delta by 3. Yes. Now, what we'll do? We'll draw the FBD of this rigid rod. Okay. Okay. What I'm doing? I'm drawing the FBD of this rigid rod. This is point O where rod is hinged. At this point, this spring whose stiffness K is coming. I'm cutting the spring from this location. At this point, this spring is coming whose stiffness is again K. I'm cutting from this location. At this point, this force F is acting in downward direction. This is A, this is A, this is A. Even if you want, you can draw this FBD in this diagram also. For better understanding, I am drawing separate diagram. Now, what will happen? At the location where spring is coming, spring force will come. Now, how we can apply spring force? First, I am applying spring force for this location. So, see, stiffness of this spring is K. Its deflection is delta 1. So, can I say here spring force will be K delta 1. Whatever direction, if you are drawing the FBD of rod, you can always remember like this. This spring force will always be opposite to the deflection. Right now, this deflection is occurring in downward direction. Yes. So, spring force will be opposite to this. So, it will be in upward direction. Very simple. Okay. Similarly, what about spring force here? Stiffness of this spring is K. Its displacement is delta 2. So, spring force will be K delta 2. It will be opposite to delta 2. Again, you can see delta 2 is downward. So, it will act in upward direction. Very simple. Clear? Now, at O, rod is hinged, and we know at hinge support always force reactions comes. So, suppose the force reaction of hinge support is like this. Okay. But don't bother about the reaction which is coming at hinge support. Reason? Can I say in this FBD system will be in equilibrium because we are calculating static deflection. And in equilibrium system, you can always use the equation of equilibrium. Equation of equilibrium is summation of force will be 0. Similarly, summation of moment about any point will be 0. So, what we'll do now, in this FBD, when you are using equation of equilibrium, will always take summation of moment about hinge point and equate with 0. Now, what is the benefit to taking summation of moment about hinge point? Can I say the moment of reaction which is coming at hinge about hinge will always be 0? So, because formula to calculate moment due to force is force into perpendicular distance. So, if you are taking moment of reaction which is coming at hinge, can I say their moment about hinge point will be 0 because their perpendicular distance from hinge point is 0. So, since moment of reaction at hinge about hinge will be 0, so if you are taking summation moment about hinge, you need not to bother about the reaction which is coming at hinge. So, this is the benefit. So, always take moment about hinge point equal to 0 because moment of reaction which is coming at hinge about hinge will be 0. So, we need not to bother about the reaction which is coming at hinge. Now, take the moment of other forces. So, first I am taking moment of this force F about hinge. So, it will be F into its perpendicular distance from O. F is vertical, so horizontal distance from O, it is 3a. So, moment of F about O, that is hinge point, will be F into 3a. Now, what about direction? You can see this force is like this. About O, it is rotating clockwise, means it is clockwise movement. Okay. Now, suppose whatever first direction of movement is coming, it is clockwise. For that, I am using plus sign. And if for clockwise you are using plus, then for anti-clockwise use minus. It is your will. If for anti-clockwise you are using plus, then for clockwise use minus. Right now for clockwise I am using plus, so for anti-clockwise I will use minus. Now moment of this force about O, so this force is K delta 1. Now its perpendicular distance from O, it is vertical, so horizontal distance, it is 2a. So moment of this force about O will be K delta 1 into 2a. Now what about direction? This force is like this. Now how it is rotating about O? About O it is rotating like this, which is anti-clockwise. For clockwise I am using plus, so for anti-clockwise we will use minus. Now moment of this force about O, so this force is K delta 2, its perpendicular distance from O is A, so its moment about O will be K delta 2 into A. Now how it is rotating about O, so this force is like this, about O it is rotating anti-clockwise, for clockwise we have used plus, so for anti-clockwise we will use minus. Now moment of reaction at O, about O will be 0. So we need not to bother about the reaction which is coming at O. Okay. So this is total summation of moment about O, which is equal to 0. Now just solve this. We calculated the expression of delta 1 and delta 2 in terms of delta. Na? So it is F into 3a minus K delta 1. Delta 1 is 2 by 3 delta. So it will be K into 2 by 3 delta into 2a minus K delta 2. Delta 2 is delta by 3. So delta by 3 into a, that is equal to 0. So it will be F into 3a minus, it is 2 to the 4. So it is 4 by 3 K delta a minus 1 by 3 K delta a. Okay. Now minus 4 by 3 minus 1 by 3. Ultimately it will be minus 5 by 3. Calculation is your partner. K delta a, that is equal to 0. So it is F into 3a, that is equal to, this minus will come this side, it will become plus 5 by 3 K delta a. Now this a and a will get cancelled. Now from this try to find F by delta. We will calculate F by delta, it is coming. Delta will come this side, it is 5k by 3. This 3 will come below side, it will become 5k by 9. So if you are calculating F by delta, it is coming 5k by 9. And F by delta is nothing but equivalent stiffness, that is K. Okay. So for this system, equivalent stiffness K is coming 5k by 9. Equivalent stiffness means we are replacing this entire system with single spring whose stiffness is Ke, and below this we are applying this mass M. And for this case, Ke is 5k by 9. Clear? And after calculating Ke, I can calculate omega n, because omega n is root over Ke, which is 5k by 9 upon the value of point mass, which is M. So natural frequency of this system in radian per second is this, root over 5k by 9M. Clear? So if spring are neither in series nor in parallel, but if they are satisfying this two conditions, that is only one point mass is there and restoration is only due to stiffness, it is not due to gravity. In that case, you can always calculate omega n by using this Ke method. Clear? Yes. Okay. So if similar type of question is coming, you will be able to solve. Na? Good. Okay. Now in this category, I am discussing one more cases. Okay. For this case, I will not do the derivation. Whatever final conclusion is coming now, because that we have to remember. So I am not going into derivation. See. Here now, don't say it is general case, because one spring is directly attached to the mass. Okay. So it is general case, omega n will be root k by m. No. Try to recall. When I was discussing general case, what I was saying, spring should directly attach to the mass. After that, mass should vibrate in the direction in which spring is aligned. After that, diagram is horizontal, vertical, inclined, doesn't matter. But see, here mass is vibrate in this direction, horizontal direction. But spring is not aligned in horizontal direction. So it is not. If diagram is like this, na, see. It is general case. It is general case. Because diagram is inclined, doesn't matter. But here mass is vibrating in the direction in which spring is aligned. So for this case, if you are calculating omega n, it will be root k by m. But this is not general case. Reason, it is correct. Spring is directly attached to the mass. Oh, sorry. It is correct. Spring is directly attached to the mass. But mass is not vibrating in the direction in which spring is aligned. So what we'll do? For this case also we'll draw equivalent diagram. I am directly discussing how to draw equivalent diagram. Just remember that. See, whenever the spring is directly attached to the mass, but mass is not vibrating in the direction in which spring is aligned, in that case we'll draw equivalent diagram. How will draw equivalent diagram? This type of question has come in aerospace, na? That's why it is important. In equivalent diagram, na, the spring which are not aligned in the direction in which spring is aligned, na, what I will do now, will replace this spring with equivalent string, and that equivalent spring will align in the direction in which mass is vibrating. Right now mass is vibrating in horizontal direction, so we will align this spring in horizontal direction. So what we'll do now, first see the angle of this spring, or you can say smaller angle. You can take any angle, but I will suggest take a smaller angle of this spring from the direction in which mass is vibrating. So from the right now mass is vibrating in horizontal direction. So see the angle of this spring from horizontal direction. Right now it is theta. Okay. Don't remember like this that always will take the angle of spring from horizontal. No. I am taking the angle of this spring from the direction in which mass is vibrating. Right now mass is vibrating in horizontal direction. That's why I am taking from horizontal. If mass will vibrate from vertical direction, then I will calculate this angle from vertical. Okay. And if this mass is vibrating in this direction, then no issue, because in that case you need not to draw equivalent diagram. If mass is vibrating in the direction in which, in that direction, if spring is not aligned, in that case I will draw equivalent diagram. And to draw equivalent diagram, what is the method? First see the angle of this spring, or small angle of this spring from the direction in which mass is vibrating. Right now mass is vibrating in horizontal direction, so see angle from horizontal direction, it is theta. So now what we'll do, in equivalent diagram, I will replace this spring with equivalent spring, which I will apply in the direction in which spring is aligned. Right, sorry, in the direction in which mass is vibrating. Right now mass is vibrating in horizontal direction. So now in equivalent diagram, align this spring in horizontal direction. And in horizontal, why I am aligning this side? Because I have taken angle from this side. Okay. Now, but I will change the stiffness. Original stiffness is K. So now the stiffness of this equivalent spring will be K cos square theta, where theta is the angle of this spring from the direction in which mass is vibrating. Okay. So this is the equivalent diagram. Now this diagram is diagram of general case. So can I say for this diagram K is K cos square theta. So now you can calculate omega n. Omega n will be, now you can tell K, because it is like general case, na? K cos square theta. So omega n will be root over K, which is K cos square theta upon the value of m. Okay. Okay. I am not going derivation. How you come to know here K is this? So again in this diagram we will apply F in the direction of vibration, then in horizontal, and we will calculate static deflection of this point, that is delta in horizontal direction, and we will calculate this expression F by delta. I am 100% sure it will be equal to this. but you need not to go in derivation, just remember this. Now in GATE Aerospace, this type of question has already come. This spring is K, whose stiffness is K. Again, this is spring whose stiffness is K. Here mass is aligned. It is vibrating in vertical direction. This angle is 45 degree. This angle is 45 degree. Our objective is to calculate omega. If you calculate omega, you can calculate frequency in hertz also. You can calculate time period also. So how will calculate omega? Here I am discussing the solution. It is very simple. Here spring is directly attached to the mass, but problem, it is not aligned in the direction in which mass is vibrating, because mass is vibrating in vertical direction, but spring is not aligned in vertical direction. So how will draw equivalent diagram? See, mass is vibrating in this direction. So what I will do? This spring I will replace with equivalent spring, which I will align in vertical direction. Why in vertical? Because mass is vibrating in vertical direction. For that, see the angle of this spring or smaller angle from vertical. Smaller angle of this spring from vertical is 45 degree. Okay. So in equivalent diagram, align this spring in vertical direction. And since from vertical we have taken angle from this line, so align this spring in this direction. Okay. Now replace this spring with equivalent spring whose stiffness will be, this stiffness is K, its angle from vertical is 45. So equivalent stiffness will be K cos square 45 degree. Now cos 45 is 1 by root 2. So its square will be 1 by 2. So it is nothing but K by 2. Same. Replace this spring by equivalent. For that, see the angle of this spring from vertical, it is 45 degree. So again, I will align this spring in vertical direction like this. And I will replace this with equivalent stiffness, which will be K cos square 45, which is K by 2. So this is equivalent diagram. That's it. Now after that, you can see these springs are aligned in the direction in which mass is vibrating. So now I can use series parallel arrangement. Okay. And they are in parallel arrangement. So now I can calculate overall K equivalent. Suppose this is 1, this is 2. Now in this diagram, can I say 1 and 2 are in parallel? I am not saying these two springs are in parallel. I am saying these two springs are in parallel. And since they are having parallel arrangement, so you can use their calculate their equivalent, and their equivalent is overall K equivalent. So I can directly calculate K equivalent. It will be equal to K1, which is K by 2, plus K2, because they are in parallel. That's why I am adding there, which is again K by 2. So K is coming K. And after calculating K, I can calculate omega n, because omega n is root over K upon the value of point mass m. Now K is K, so omega n is root K by m. Clear? So like this you can proceed. Okay. So this method is nothing but equivalent stiffness method. Clear? Yes. Good. Okay. So till now I discussed, see, till now I discussed what is natural vibration of free unending vibration. Then we have discussed this free unending vibration of general spring mass system. After that, we have discussed free unending vibration for those cases in which you can use equivalent stiffness, that is 𝐾𝐸 method for calculation of omega n. Those cases are the cases in which only one point mass is involved and restoration is occurring due to stiffness. But apart from this, if any other case is coming, any other case means either more than one mass is involved, or mass is not point mass, it is distributed, or restoration is not only due to stiffness, it might be possible it is due to gravity also. In that case, I cannot use this 𝐾𝐸 method. So in those cases, what we will do? We need to derive the equation of other cases. So we need to derive the equation of vibration. So for other cases, now when I am saying now other cases, means I am talking about those cases in which this 𝐾𝐸 method is not also valid. Reason? Either more than one mass is involved, or restoration is not due to stiffness only, it is occurring due to gravity also. So in those cases, I need to derive the equation of vibration. And to derive the equation of vibration now, okay, and when you will derive the equation of vibration, it will always be like this. like this. Only we need to calculate the coefficient. Right now, I don't know what will be the coefficient of x. Suppose coefficient of x I am denoting as Ke, coefficient of x double dot I am denoting as Me. Don't say Ke is stiffness, Me is mass. No. For general case, Ke was K, Me was M. But for other case, what will be Ke and Me, that will come to know after derivation. But pattern of equation will be like this. It doesn't necessarily always x and x double dot will come. Here, if it is theta, it should be theta double dot. Again, I will refer coefficient of theta as Ke, coefficient of theta double dot as Me. Then omega n will be root over Ke by Me. Here, if it is phi, it should be phi double dot. Here, if it is theta 1, it should be theta 1 double dot. Then omega n will always be root Ke by Me. This we already discussed, na? But for Ke and Me, first I need to derive this equation. And to derive this equation, again we are having two methods for natural vibration. Okay, so method to derive the governing equation of natural means pre-undone vibration. And right now we are discussing single degree of freedom system. Na? We had two methods. One is an equilibrium method and second one is energy method. Both methods are simple. But with equilibrium method, how we can derive the equation of vibration? With energy method, how we can derive the equation of vibration? Okay. This discussion I have already done on the YouTube. Okay. So there is no benefit in repeating the same concept again. Na? You will see this GATE Wallah English YouTube channel. Na? It will go in the playlist, vibration playlist or structure playlist. You can go. Okay. In that playlist, you will find one lecture. Tomorrow I will bring the link of that lecture also. You will find one lecture, that is the rotational vibration. Search on YouTube. Na? In YouTube, search GATE Wallah English channel. In that channel, if you go in the playlist, you will get the playlist of structure by me, or you for aerospace, or you will get the playlist of vibration. Okay. In that playlist, you will get a lecture having name rotational vibration. Okay. In that lecture, I had discussed these two methods, equilibrium method and energy method. So I will suggest watch that lecture. There is no benefit in again repeating the same discussion. Na? So in that lecture, you will find these two methods. Okay. So now can I say I have completed the discussion of natural vibration of single degree of freedom system, because I had discussed introduction part. I discussed this vibration for general case. I discussed this vibration for those cases in which is not general case, but you need not to derive the equation of vibration, which you can solve by equivalent stiffness method. Those cases are the case in which only 1 point mass is involved and restoration is only occurring due to stiffness. But for the cases in which this equivalent stiffness method is also not valid, for those cases I need to derive the equation of vibration. And to derive the equation of vibration, we are having two methods. One is equilibrium method, second one is energy method. These two methods I have already discussed on YouTube in this channel. If you go in the playlist of structure or vibration, you will find a lecture having named rotational vibration. In that lecture, I have covered these two topics, that is equilibrium method and energy method. So just watch those lectures in which I have discussed these two topics. So now can I say we have completed this natural vibration of single degree of freedom system. In this lecture, I discussed its introduction part. I discussed this vibration for general case of spring mass system. Then I had discussed stiffness method, this in which we had discussed how to calculate Ke. That method is valid only for those cases in which only 1 point mass is involved and restoration is occurring only due to stiffness. Okay. Then next topic was method to derive the equation of vibration, in which we have to discuss mainly two methods. One is equilibrium method and second is energy method. Okay, I will suggest for discussion of these two methods, go on this YouTube channel. In the structure playlist, you will find a lecture which is having name rotational vibration. In that lecture, I have discussed these two methods for natural vibration. Okay. Tomorrow, I will discuss free-band vibration. Free-band vibration. Okay. Okay. But to understand the tomorrow class, first come with the revision of this class. Revision means discussion which I had discussed till this point, and also watch this lecture rotational vibration, in which I had discussed these two methods. Then tomorrow I will start pre-band vibration. I think, is it clear to everyone? Please confirm. Okay, thanks. I am ending the class now. Tomorrow I will discuss free-band vibration. Okay. Ending.